A grid-scale capacitor bank stores significant energy that, if released through a fault, can destroy equipment and destabilize the local network. Before these units can be integrated into the active grid, they must be cleared through a rigid validation sequence. Safety is managed through a sequential de-risking progression. The procedure is divided into two distinct 8-step scripts, the first for dead-state dielectric verification and the second for controlled live-state validation. This progression follows a globally recognized reference framework. Testing must align with the standards of the IEC, IEEE, ASTM, NEMA, ANSI, CI-GRAY, ICEA, and KEMA to ensure the hardware meets its design tolerances. As shown in the header of the commissioning manual, project-specific procedures are codified alongside these international standards. If a project's specification, manufacturer instruction, and standard differ, engineers apply a strict governance rule. They must default to the most stringent approved requirement. Commissioning is a regulated de-risking operation. By resolving discrepancies at the documentation level first, the team ensures the actual field testing is technically grounded. The foundational safety axiom for the entire procedure is that a capacitor holds a lethal charge until it is mechanically grounded and verified. This banner details the 5 mandatory safety precautions. The area must be tagged and isolated, personnel must keep a safe distance, wear arc flash PPE, and implement proper grounding before any measurements begin. Once secured, the standard loadout includes fluke multimeters and clamp meters for basic continuity and current checks, alongside manual discharge sticks. For deeper dielectric profiling, the team uses specialized equipment, a power factor or tan-delta test instrument, and a high-voltage insulation resistance tester. These tools are specifically designed to expose microscopic physical defects. They identify early degradation in the hardware before those flaws result in a dielectric breakdown under high-voltage loads. Work begins with step 1 of the initial 8-step dead testing script, setting the LODO boundary. The team reviews the switching order and applies safety warning tags to ensure the bank remains isolated from the grid. Step 2 requires verifying the final isolated and discharge status of every capacitor unit. This confirms the absence of stored energy before personnel handle the equipment. Step 3 is a detailed mechanical check. The team inspects the structure, insulators, fuses, and neutral circuits for damage. They look for microcracks on bushings or structural corrosion. Contamination here can cause tracking faults, leading to flashovers upon energization. Mechanical integrity is the mandatory prerequisite. If the structure is compromised, any subsequent electrical testing is considered invalid. Step 4 is the insulation resistance test for all phases. After each DC mega measurement, units are discharged to clear dielectric absorption charges. In Step 5, tuning-reactor inductance is measured. Readings must meet exact tolerances to prevent unwanted harmonic resonance. Step 6 is the dissipation factor test. By measuring the ratio of resistive to capacitive current, engineers evaluate internal dielectric purity. As shown in the phasor diagram, the angle delta represents the energy lost as heat within the insulation. Step 7 involves measuring internal resistance and capacitance for every unit. This allows engineers to cross-reference with the external resistors and detect any capacitance mismatch that could cause an unbalance. These discrete dead-state tests mathematically map the health of the bank. By completing the first 8 steps, the team ensures the asset is physically ready for voltage. The transition from Step 8 of the first script to the live testing sequence is marked by a mandatory hold point. A witness must verify the accepted results and sign off on safe discharge status before proceeding. Energizing a capacitor while it holds a DC charge creates high-magnitude transient overvoltages. This can cause immediate equipment failure and risk to the substation. To mitigate this, the framework mandates residual voltage decay to 10% or less of the rated voltage before re-energization. Step 8 confirms the residual voltage and unbalance-relay circuits are connected and primed to read this decay during the on-load phase. Clearing this 10% threshold is the final physical barrier between the safely grounded hardware and a grid-connected system. We move to live state validation. The team connects a 3-phase AC source and diagnostic meters, as defined in the schematic. Under controlled conditions, the source is energized, and engineers monitor phase voltage and current continuously. This ensures the bank responds predictably as it accepts the load. The definitive evidence of a healthy bank is found at the neutral CT path. In a perfectly balanced system, the clamp meter reading for unbalanced current should be exactly 0. This 0 reading proves every capacitor element possesses identical impedance, confirming a symmetrical, stable bank. Neutral unbalance is the primary diagnostic for live operations. Any non-zero value indicates an individual unit has degraded and is pulling the system out of balance. By simulating an imbalance, the team confirms the protection relay will trigger alarms and trip the circuit breakers. If the relay fails to respond, commissioning is halted. Engineers must perform a wire-by-wire audit of the neutral CT and VT references to find the error. If residual voltage exceeds the 10% limit, no energization is allowed. The team must wait for the internal discharge resistors to bleed off the charge or manually apply grounding sticks to reach a safe state. If the neutral current is greater than 0 during testing, the bank is immediately de-energized. The imbalanced phase is isolated for a full remeasurement of every internal unit. There is 0 tolerance for these deviations. Anomalous readings require the team to regress through the procedure until the imbalance source is identified and corrected. Following a successful unbalance test, the bank is de-energized and restored to its normal operating configuration. Test leads are removed, and temporary grounding is cleared. The final evidence package is compiled. This includes all 16 steps of documentation, from the initial mechanical checks and IR sheets to the final tan delta and neutral unbalance reports. The final hold point requires operations and commissioning witnesses to confirm the relay resets and SCADA status before the bank is handed over for service. Now fully integrated, the bank supports the grid by providing reactive power, maintaining voltage levels, and improving overall system efficiency. Through this exhaustive 16-step protocol, engineers transform a complex array of high-voltage components into a verified and stable pillar of the modern electrical grid.